My great pleasure to introduce Professor Kevin Leyton Brown. Kevin, it's fair to say, is the originator of this field, unless you want to correct me on that, Kevin, on the use of machine learning in the context of solvers. I think
I'm sure
Kevin.
Moshe will send some references in the chat to correct you on that.
No, I think on this one I agree with Vijay.
Wow, nice of you, Moshe.
And so Kevin is a professor of computer science at UBC, got his PhD at Stanford, and he has won many awards for his research, including an NSERC EWR Stacy Memorial Fellowship and several other awards. So without further ado, Kevin, the floor is yours, and you may share your screen and start the talk. Thank you.
Thanks. You think I'd be faster sharing my screen by now after a year in pandemic? Yeah, I guess I made the crack about Moshe sharing the references because the truth is this field goes back a long time, and particularly into systems and all kinds of different places that kind of ML for solvers kind of cropped up before they kind of got unified into this this community that we have today. But I think it's really exciting that we're at the point where we have Simon's workshops dedicated to this topic. I think this is a really exciting thing. I'm going to speak about something a little bit less practical than we've heard from the other speakers today. I'm going to talk about using machine learning to directly predict the result that we would get from a combinatorial solver. Given the topic of the broader Simon's semester, I'm going to look at propositional satisfiability, and I'm going to survey a whole range of different work that my group has done over the years, culminating in some work on end-to-end learning, using deep learning to predict propositional satisfiability directly from raw inputs. I'm going to be throughout speaking about uniform random 3-SAT at the phase transition, not because these are the most important SAT problems practically to study. It's obviously a bit of a toy problem, but it's a very clean, well-studied problem that is sort of the fruit fly of SAT research. It's empirically hard. A lot of people have looked at it, and we have maybe the best theory about it. So it's kind of conventional wisdom that at this clauses to variables ratio of 4.26, uniform random 3-SAT problems are have a 50% chance of being satisfiable, which is true, and they're empirically hard, which is sort of almost true. Here's if we look at actual empirical performance, instance by instance, on a log scale at the phase transition point, you see that in fact. This is where this average hardness spikes, but you also see that there's a lot more variation than you might have expected. There's still really easy instances at this point as well. So some co-authors and I got interested in the sort of somewhat ridiculous question of saying, could we use machine learning to try to predict which kind of instance we've got in hand? If we were at this phase transition point, or if we had some well-defined set of instances and we wanted to take some new instance from this set and try to determine, is it going to be hard or easy to solve? And so we, in a whole string of work, I'll just have sort of citations at the bottom here, but in a whole string of work culminating in a CACM paper in 2014, we said, let's try to find some instance features of a SAT instance that we could compute in polynomial time that would give us a handle on its combinatorial structure that we could then use in a model to try to predict whether the instance is hard or easy. So the most obvious thing you might think of if you've taken a kind of undergrad algorithms class is the size of the problem. So how many clauses does it have? How many variables does it have? What's the clauses to variables ratio? Of course, these will all be constant if I was looking at the phase transition point. Then I can look at other things like syntactic properties. For example, what's the ratio of positive to negative clauses in the formula? I can then build various constraint graphs and say, such as the factor graph, the clause graph, or the variable clause graph. I can ask things like, what are the average degree statistics in the graph, or what are path lengths in the graph, or how clustered are the graphs. I can use the search space size estimate due to Don Knuth, where you look at you make sort of random probes in a sort of DPLL space and say what's the average depth in the tree, and that's an estimate of the log number of nodes in the tree. I can do look at the cumulative number of unit props that I would get at different depths using a given heuristic, like the SATC heuristic, and say how amenable to this heuristic does the formula appear to be. I can take local search algorithms, even if the algorithm that ultimately I'm interested in is not a local search algorithm, and I can say, using some bounded amount of time, what happens when I run the local search heuristic? Do I find that I quickly reach a plateau, or does it improve a lot, or how much variation do I get in the kinds of trajectories that I see in this sort of bounded local search unrollings across different random restarts of the local search heuristic. And finally, I can take a linear programming relaxation of the problem, and then I can look at the slack vector of this linear program, how far from integral the variables in linear programming relaxation are, and take like a norm of that vector or a coefficient of variation of that vector, get a sense of how close it is to integral. So we built all kinds of features like this. This wasn't meant to be comprehensive, and it certainly wasn't meant to be formal, but it gives you a sense of the kinds of things you could dream up, and you could probably dream up more. So then using pretty simple regression kinds of methods, we were able to build models that predict, that make predictions like this. So here I'm saying on the x-axis, what was the actual runtime on a log scale of a SAT solver like KCNFs, and on the y-axis, what do we predict the runtime to be? And we would like to exactly nail this diagonal red line. And what we got here was pretty good. It's always hard to sort of eyeball a scatter plot, and I could give you numbers which are also kind of hard to interpret. But we're able to do reasonably well in predicting unseen problems at the phase transition point, where the clauses to variables ratio is telling us nothing. So we found this intriguing, and we wanted to dig in. So we started saying, what if I tried to build much smaller models that I could then interpret? And we did this by using forward selection, which is a greedy way of doing variable selection in some kind of model framework. So here we were using quadratic regression. And so we iteratively added features to the quadratic regression and found that 4 variable models in this case did pretty well. So here was a good 4 variable model, and here's how much it hurt us to lose, just scaled to 100%. Here's how much it cost us to lose each of these 4 variables. And so you see the last one was the least valuable. And interpreting this, we can see that these local search probing features that I told you about were important all over the place. So every one of these 4 quadratic features that we've learned here includes one of these local search probing features. And Donald Knuth's search space size estimate feature featured in 2 of the 4, and the variable clause graph node heuristic also features in the last one. So this gives us some sense of what's going on in terms of understanding how these models are able to make good predictions. Let me shift for a minute to variable ratio problems. So here we're sampling around the phase transition, not only at the phase transition. We're able to predict much better in this point. And here I'm going to color our predictions by whether the problems were satisfiable or unsatisfiable. And you see a kind of interesting trend here that the unsatisfiable instances are predicted much more accurately than the satisfiable instances, which might make sense to you because in the case where an instance is unsatisfiable, you've got to search the entire tree, and so there's going to be much less variance across sort of random noise. Whereas the heuristic that stops as soon as it finds a satisfying assignment might be more easily manipulated by slight variation in the problem instance, and so we might get more variation in runtime. So we certainly see more variation anyway in the predictions of our models. So we were intrigued though by the great difference between the quality of our predictions for unsatisfiable and satisfiable instances, and this led us to ask whether we could build much better models if we imagined that we knew the satisfiability status of an instance. Of course, this means the clauses and variables ratio would be unimportant. And indeed, it turned out that single feature models in this case became sufficient. So when instances were satisfiable, then turns out those local search probing features that I told you about before were all you needed to make good predictions. And when instances were unsatisfiable, then those search space size estimates turned out to be sufficient to make good predictions. So, of course, we don't know the satisfiability status of an instance. If we did, we wouldn't presumably want to run a SAT solver in the first place. But this is still kind of an interesting insight maybe into how these models are working and why these two families of features turned out to be so important in our fixed variable models that we were looking at the fixed ratio models that we were looking at in the first place. So then we had a kind of audacious idea that maybe only machine learning oriented people could have. We wondered, could we build a kind of hierarchical model that would begin by predicting satisfiability status, and then it would condition on this prediction as a feature to combine the predictions of the SAT-only and unsat-only models that we had just seen worked well. Let me point out that this would not necessarily be an easy thing to do, because if we could make these predictions really accurately, we would do well. But these SAT-only and unsat-only models do egregiously badly when they're given the wrong input. So if these predictions ever went wrong, our models could potentially be terrible. Nevertheless, we showed in joint work with Ling Xu and Holger Huss back at CP in 2007 that we could do much better with this kind of an approach. So here's the same graph I showed you before on the left, and then a graph on the same data using this hierarchical hardness model approach. And you see that we really managed to reduce the variance substantially, especially visible on the unsatisfiable instances. So let me go back for the rest of the talk to fixed ratio. I just had the variable ratio problem, so I could show you this picture, which was on variable ratio. But going back to fixed ratio, for the rest of the talk, I don't want to think about predicting runtime anymore. That's really just how we came to this problem. But I want to instead really think about this question of satisfiability status. So from that work, here's the models that we had predicted at the time, that we built at the time, and here's how they worked. So these models predicted a probability of SAT. They didn't just predict a kind of discrete class of whether something was SAT or not. And you see that as the model became less certain about the satisfiability status, it also became more wrong. So the model was relatively calibrated in its predictions. We then went, again with Ling Xu and Holger Huss, into a deeper dive into trying to understand, does it really make sense to think that we could predict the satisfiability status of a phase transition instance, which we kind of believe to be a hard distribution of problems? So to try to understand this better, we tried to tie a couple of hands behind our backs and build something that would persuade us more fundamentally that this was even doable. So we considered phase transition instances that varied from 100 variables, which are problems that are solvable in milliseconds, even back in 2012 when we did the work, to 600 variable problems, which were solvable in about a day back in 2012, and now still take kind of hours. And what we wanted to know was, as the problem size is scaled up, would prediction accuracy fall to random guessing as problems get bigger? And if not, can we identify some easily comprehensible model that would offer theoretical insight into what was going on? And this sort of experimental setup was inspired by conversations with some theorists, I think in part at Simons, who wanted to, you just didn't believe that this was really going to be possible to do. They thought it might just kind of be a small size effect. And of course, because all of our experiments are empirical, I can't really ever say that this isn't a small size effect, because whatever finite size I look at, you can always tell me is small. But here's the best I can do to try to argue that this isn't a small size effect. So what we did is we trained only on these millisecond solvable instances, the 100 variable instances. The reason we didn't go even smaller is we didn't want problems that were solvable in cache. We wanted them to involve some amount of search, so that they would be in some sense representative of larger instances. We considered only models that use decision trees with at most 2 decision nodes, and we turned off all probing features. So probing features are things like the local search probing, like Donald Knuth's search space size estimate, like the use of the SAT-Z heuristic to look at unit propagations, all of these kinds of things that run solvers for a bounded amount of time, because using bounded amounts of time isn't going to scale from one size to another. We wanted instead features that looked at some kind of structural property of an instance that would be well defined from one size to another, so that we would believe that it would actually capture something combinatorial about the instance. And we wanted to see, would it still be the case that we could build something that would do well on larger instances? And to our surprise, we found that it actually worked really ridiculously reliably. So here is a simple model that beat random guessing, and it achieved predictive accuracies of around 70%. Bearing in mind that 50% of the instances were satisfiable and 50% were unsatisfiable. So random guessing would get you 50%. And we were getting 70%. I don't recommend you throw out your SAT solver and use this model instead. But, and by the way, I should also stress to you, this model doesn't give you a certificate of satisfiability. It just gives you a guess, which is 70% accurate. But I think it says something about the learnability of this class of problems nonetheless. And I think it offers some interesting kind of grist for theoretical insight. So here's what the model did. It said, first of all, let me look at one feature to do, and I'll say more actually in the next slide about what these features were. Well, actually, maybe I'll go into the features in a second. Let me just say what's on this slide. So let me stress to you, we trained this model only on 100 variable problems, and then we evaluated it on problems going all the way up to 600 variables. And we saw no evidence that accuracy fell with size. In fact, if anything, accuracy seemed to improve very slightly with size. Let me show you here what the features were. So, by the way, I see in Zoom evidence that something is happening in the chat. I can't see the chat while I'm sharing my slides. I'm very happy to be interrupted by questions. So if anyone has anything that would be fun for us to talk about, maybe even let me pause now and see if anyone wants to interject.
Actually, I do have a question.
Yeah, please go ahead.
And it has to do with the features that you used in this predictive model. So you said you didn't use probing features. Probing features, just to remind us, are features that are about the run of the solver, right? So is that fair?
Yeah, so probing features are, take some solver and run it for a bounded amount of time.
Okay. And here, these were all quote unquote like structural features, just formula features, if you will, right?
Sure.
And could you tell us what those features were and how many of them did you use to construct your model?
So you're looking at the model.
Okay.
The model is this decision tree. It is a 2-node decision tree in 2 features. And this slide exactly defines what those features are.
Okay.
So the model says, let me compute the coefficient of variation of the LP slack vector, which I'll define in a second. If it's bigger than 4 thousandths, then return sat. Otherwise, look at this feature that has to do with the ratio of positive to negative occurrences of variables. And if that's a little bit unbalanced, then return sat is again, and otherwise return unsat. That's the entire model.
And it's able to give you 70% predictive
Yeah,
power.
isn't that crazy?
Yeah. Now, did you try to apply this to kind of structured classes of instances as well, or only to random?
Yeah, we have looked at some structured classes of instances. It's difficult to find structured classes of instances that are exactly 50-50 sat unsat, so that tends to make the prediction problem easier. Right. So one reason why this is a nice kind of test set for us to look at is that it kind of is about as hard as possible to sort of cheat at. But yeah, we haven't found that this sort of phenomenon is restricted to uniform random 3 sat.
I'm assuming subsequently you're going to talk a little bit about SatZilla as well, where you considered a much larger set of features to where you're using it for algorithm selection, but there you're predicting runtime as opposed to satisfiability.
I'm not actually. For the rest of this talk, I'm not going to speak at all about runtime prediction again. But I guess I'll say that this two-node decision tree was based on this set of maybe almost 100 features, kind of from this space, having thrown out the probing features. So it isn't that I only gave it those two to look at. Those are the two that it picked out of a much larger set. And indeed, this is the set that we used for SatZilla and for SMAC and some other things as well.
Thank you.
Cheers. Sorry, so let me go ahead to this result. This first feature, so we're only using 2 features, but let me say the features are a little computationally powerful, right? So the first feature is based on solving a linear programming relaxation of the SAT problem, which takes sort of roughly cubic time. So you solve this LP relaxation, and then you look at the variables in the LP relaxation, and you ask how close they are to being integral. So you make a variable, a vector for each of these variables saying how close it is to integral. And then you look at the coefficient of variation in that vector. So although that's only one feature, it's kind of doing a lot of work. So that's kind of interesting, right? This is telling us that the amount of variation in the slackness of this LP is telling us quite a lot about whether uniform random 3 sat is going to turn out to be sat or not. In those cases where there isn't very much variation, conditional on that variation being low, then we look at this ratio of positive to negative occurrences of variables. We look at the mean ratio, and when that mean ratio skews high, then again we tend to think that the instance is sat, and otherwise we tend to think it's unsat. When you look at these numbers that are both kind of a little bit bigger than 0, what do they mean? It's important for you to say that these features are normalized to have mean 0 and standard deviation 1 on the training set. So we're saying that they're bigger than average, right? 0 would be average. And this is a big, I don't want to lose this detail, this is a big part of why our models were able to generalize. So when we evaluate on instances of a new size, this normalization would presumably change on a new size. So here's how we do that without cheating. I have a model that was trained only on 100 variable instances, and then you give me like a 700 variable instance that I've never seen before. I don't know what the normalization is to get back to mean 0 and standard deviation 1. So what I do is I generate many, many instances at that size, which I can do because it's uniform random 3 sat. I can generate anything I like. I don't solve those instances. I just generate them. And I use them to sample, and I compute the features on them, which I can do because the features are cheap to compute. And I use those to estimate the normalization factors. And then on my one test instance, I use those normalization factors that I got from the many instances that I generated and threw away. And I use those factors to compute the features for the test instance, and then I make a prediction from the test instance. So I don't solve anything at the larger size, but I do compute features from anything so that I can normalize them. So that's an important detail about how we're able to generalize. Okay, so now let me tell you about work from much more recently, from last year. So as the question just indicated, everything that we were doing so far depended on these features that we had to kind of make up based on insight about SAT. So I had to know that the LP relaxation of SAT was a thing and that it might be useful for something. And, you know, it's kind of crazy. Most people don't think the LP relaxation of SAT is any good. So what if I didn't have it? You know, then I would have come up with something completely different. You know, what if something else is also really good and I didn't have that? How would I ever know? Well, you know, these days, the whole kind of learning landscape has changed from using features to end-to-end learning using deep learning, and has really transformed the state of the art in a lot of different ML applications. So we became intrigued by thinking about whether we could predict satisfiability status end-to-end, taking raw problem representations as inputs, you know, just as has been possible in other domains. This is joint work with my students, Cameron Chen in Hartford, and Chris Cameron, the lead author on this, is also a visitor in this Simon semester. So I encourage you to reach out to him if you're interested in this work. So let me just say, you know, end-to-end learning, you know, people talk about it being kind of totally end-to-end. Let's take an example. You know, there's a little bit of a fly in that ointment. So let's think about computer vision and how that worked. In computer vision, you know, it used to be that feature engineering was the name of the game. You know, David Lowe, who used to be in my department, made his career on having come up with a set of features back around the turn of the millennium for machine vision. He got like 80,000 citations for these SIFT features, which now, you know, a day on a GPU with a neural network will produce you something like the SIFT features. So now features just get identified automatically with these deep architectures, but the catch is you need to give them the right structural assumptions or inductive biases in the machine learning. And it turned out that in vision, the right inductive bias was convolution, which corresponds to translation invariance. So, you know, the picture of the puppy is the same picture of a puppy, no matter where you slide it around in the vision, in the kind of viewport. You know, that dramatically lowered the number of parameters that you needed to learn and made deep learning for vision practical. So what would be the right structural property for us to impose on a SAT formula represented in conjunctive normal form? Well, convolution would not be appropriate for SAT because there isn't a notion of locality, right? Convolution says, you know, when you're looking for a picture of a puppy, you only have to look at the pixels that are all close together. And when you slide them around, it's the same picture. Well, with a SAT formula, you can sort of garble it all around and get the same SAT formula. So locality is not the important thing. So in SAT, the key insight is that the formula is unchanged by renaming variables or reordering clauses, because the and or operations in the CNF are commutative. So we want to say that the input to a SAT formula should be represented as an exchangeable matrix. So what happens if I tried to use a standard feed-forward layer of a neural network on an exchangeable matrix like this? Well, typically what you would most naively do in machine learning is you take your exchangeable matrix and you'd vectorize it. Then you define your feed-forward layer as some nonlinear activation function sigma applied to a weight matrix multiplied by this vectorized input x. And you know, the dimensions of this thing would be n times m by k, where k is whatever number of neurons in the next layer that I want to feed forward to. Notice that this is going to treat every permutation as being different because I've got you know, different weights everywhere in this matrix, and this is going to violate the invariance property that we want. So something that you might want to do if you wanted to enforce invariance, a way you might think about enforcing invariance would be to tie parameters in matrix W so that they're all the same under every permutation in order to enforce this permutation invariance. So what would happen if you do this? Well, if your input is a set, it turns out that you only get to have 2 free parameters per channel, which is to say per output neuron that you would achieve. this result was achieved by a couple of different papers, but most thoroughly by Manzil et al.'s deep sets paper. In follow-up work to that work, with some co-authors, notably my student Jason Hartford, Devin Graham, and C.I. McRavenbosch, we showed that if X is an exchangeable matrix, then you only get to have 4 free parameters per channel that correspond to one parameter for the same element, one parameter for all elements in the same row, one parameter for all elements in the same column, and one parameter for everything else. Now, this forced us to represent this weight matrix explicitly and then to do a matrix multiplication, which is expensive for the feed-forward pass in the network, and thus makes training the network really expensive. But it can be efficiently implemented by you making some commutative pooling operations. And this causes the runtime to scale linearly with a number of non-zeros in the input matrix rather than requiring this matrix multiplication. So we can say compute a one pool across every row. I keep doing vertical rows for some reason. One pool across every row, one pool across every column, and one pool across all elements in the matrix. And notice that when we're not representing W explicitly and we're just speaking about pooling across rows, columns, and matrices. Oh yeah, please go ahead.
This may be a good time to maybe go back a slide because I really want to understand what you're saying here.
Yeah, sure.
I understood the problem that you mentioned, which is actually, can you go back one more slide?
Yeah.
Yeah.
Right.
So
who's
here,
speaking? Everyone else can probably see who it is, but I don't see it.
Oh, sorry, it's me, Vijay.
Oh, hey, Vijay, thanks.
Hey.
That's what I thought. But
okay, so the issue here is, you vectorize the input formula, right? And then you're doing this multiplication with this matrix here, but the problem is that it violates the permutation invariance that's associated with Boolean formulas. So in order to fix that problem, you tie the parameters in W to enforce. What do you mean by that, type of parameters?
So what I mean is, so I want my W instead to look like the W on the right. So this kind of crazy quilt structure here is a way of saying I only want to have 4 possible parameter values. So I don't know. Can you see my mouse moving around?
Yeah.
Yeah. So never mind this. This last column here is X, right? So this the rest of this thing is W, and there's only 4 colors in W here. So what I'm trying to say is W is only really allowed to have 4 distinct numbers in it, which are defined by these 4 colors. And then I'm going to take these 4 numbers and build them out into a W that's structured like this. So one parameter is going to be on the diagonal, and that's going to it was important here that I said consider the case of k equals n times m. So I'm trying to build a next layer that's the same size as my my input. So I've got a square matrix here. So I've got one element here that's the diagonal. So that's saying for every element, I'm going to give back the thing that I got. And so permutation means that's going to have to be the same everywhere. So that if I permute something, no matter where it is, I'm always going to give back the same thing that I got. And that's sort of the easiest one to see. But similarly, everything in the same row, everything in the same column, it's got to behave the same way under permutations. So if you think about what happens if you sort of start with an unconstrained matrix and sort of play the game as I permute rows and columns, I don't want anything to change in the output when I do a permutation. What does that mean about what has to get tied? You end up with a picture that looks like this. These are the only degrees of freedom that you're allowed to have if you want the same thing to happen under every permutation.
Yeah.
And then this is just a way of saying, given that I really only have these 4 parameters and then building out this W implicitly, surely I don't really need to build out this actual matrix and do a matrix multiplication that was all based on 4 numbers. Surely there's some implicit way that I can get the same answer out. And indeed we can, by just kind of taking sums and just storing these numbers based on sums. And the last point that I was wanting to make, which is important, so let me return to it, is now I actually don't really have dependence on the size of the input, right? Notice with the feed forward thing, I actually had this explicit W matrix that was n by m, right? So it really cared about the number of clauses and variables. My whole model was trained based on a particular number of clauses and variables. But now I've only got 4 parameters. 4 is a constant. It doesn't depend on n or m. So once I have this implicit representation, you can actually give it a SAT formula of a different size than it was ever trained on, and you can evaluate the model on it. Notice the standard feed-forward architecture just kind of barf on that. It doesn't even understand what that means. It doesn't have the right number of parameters to evaluate something with a different input size. But as a kind of side effect of having enforced permutation equivariance, we get the ability to evaluate on different size inputs for free. It doesn't mean it would necessarily do something sensible, but it doesn't break if you give it something of a different size. And this ICML paper with Jason, Devin, and Siamak culminated in a theorem that said that this is sort of maximally expressive if what you want is permutation equivariance. So you can't satisfy permutation equivariance with more than 4 free parameters. So this is kind of an argument that these exchangeable matrix layers amount to a kind of convolution for exchangeable matrices. It's the most expressive feed-forward layer that you can have that respects these equivariances. Let me note that since we did this work, graph convolution networks, GCNs, have become popular, and they're just really kind of a different route up the same mountain. They're also as expressive as what I've just defined. If this is your favorite family of models, go for it and use them. We built on the thing that we previously did, but we haven't seen any particular reason why one is better than the other. And that builds from the fact that the variable clause graph, the bipartite variable clause graph, is a equivalent representation to this matrix that I've been talking about. So now I'm talking about this work with Cameron et al. From AAAI. Here's the architecture that we use to do satisfiability status prediction at the phase transition. So previously I talked about a model that had 2 features, right? 2 parameters, those weights that I showed you, and got 70% accuracy. Now, here's what you would do if you didn't care about how many parameters you possibly had, but you want to go end to end. So here we have this architecture with these exchangeable matrix layers. We have 128 channels each, which means we do those exchangeable 4 parameters per channel models 128 times, and then we stack those 8 deep. So that gives us 4,096 parameters. And we set our activation function to leaky ReLU, which is like ReLU rectified linear units, but where you have a slight downward slope instead of a constant 0. Never mind if you don't know what that means. We pool over rows and columns, and then to flatten out into this pooled problem representation, 1 real value per channel. And then we build a decoder on this kind of embedding that is a standard feed-forward network of 32 neurons per hidden layer, and eventually pop out at a single real value between 0 and 1, which is our prediction of satisfiability status. And we trained it using binary cross-entropy loss. So long story short, we did this. We inconvenienced a lot of electrons on a GPU for a really long time, training this on a gigantic number of SAT instances, again, looking only at 100 variable problems. And then we evaluated them on larger problems, again, between 150 and 600 variable problems. And here's the accuracy that we got. So we see that here, even though we didn't benefit from having these features, which is a really tremendous benefit, we were able to get accuracies more nearing 80%, and actually coming up to 81% on the 600 variable problems, although maybe that's a bit of an outlier, which took hours to solve using this exchangeable architecture. And just for comparison, here's how those handcrafted features did. This is using all handcrafted features, not just the 2 handcrafted features. So it's a little bit bigger than you saw before. But using any handcrafted features, we're on average 7% worse than these exchangeable models. And
So
here's another.
We may have to wrap up in a couple of minutes.
No problem. I'm actually almost done here. I have only one slide after this.
Thank you.
This dotted line here is saying, what if I was to train and test on problems of the same size? So you see that if you wanted to target particular sizes, you do better than if you have to generalize across sizes, but it doesn't dramatically change the story. And here's the last thing I want to say. If you the other benefit of these exchangeable models is that they're dramatically cheaper to evaluate. So recall that our handcrafted features required cubic time. They required solving linear programs on every input, and that scales badly as problems get bigger and bigger. These exchangeable networks, you saw how they work. They're just kind of linear algebra running forward. It's all linear time. So they basically didn't take, they're really cheap, and they didn't take appreciably longer time as we got bigger and bigger. So this could matter in some applications to be able to build models that are dramatically cheaper to evaluate at runtime. Although I don't want to sweep it under the rug, they're also dramatically more expensive to train offline. So they took kind of days rather than minutes to train offline. So let me leave it there. So I've showed that it's possible to use machine learning to predict satisfiability status of unseen SAT instances considerably better than random guessing on uniform random 3-SAT. We're able to build models on tiny SAT instances and generalize them well to much larger instances. In particular, we showed that we could train on 100 variable problems and saw little loss of accuracy on 600 variable problems. When we train using hand-tuned features, we can examine our models to gain theoretical insight, and we were able to build a very accurate model that needed only 2 features